So an electromagnetic wave in this case is entering from air to a medium, where the electric field in the air is given to you and the electric field in the medium is also given to you. Now it has been mentioned in the problem that K and nu are the wave number and frequency of this electromagnetic wave in air. Okay. Now given that the medium is non-magnetic, you have to find out the ratio of the relative permittivities of air to the medium. Okay. So this question is based on wave equation, EM waves, and obviously relative permittivity. So in this case, you know that the relative permittivity of air is 1. So to find out the ratio, you just need the value of the relative permittivity of the medium. So let's analyze the equations. Now can you see that if you compare this equation with the standard wave equation, that is E is equal to E naught cos, and can you see that 2 pi nu is omega, right? So this is omega z by v minus t. So the electromagnetic wave is traveling along z axis and the electric field is along x direction, which is perpendicular to the direction of propagation of this wave. Now can you see that in this case the speed of the wave, that is v, by comparison is the speed of light c, right? Now let's look at the equation of the electric field in the medium. Now if you compare this with the standard form, that is E is equal to E naught K dash z minus omega t, then can you see that in this case K dash is equal to 2k, right? So the wave number in the medium K dash is twice the wave number in the air for this electromagnetic wave. Now if you assume the wavelength of the wave in the medium to be lambda dash, then you can see from here that 2 pi by lambda dash is equal to 2 into 2 pi by lambda. The frequency of the wave is not going to change as it changes the medium, right? So we get lambda dash to be equal to lambda by 2 from here. The wavelength in the medium of this wave has been reduced to half, right? And we know that the speed of the wave is wavelength into frequency. The frequency doesn't change. This means that the velocity of the electromagnetic wave in the medium is c by 2, right? And now with the help of this, we can find out what is the relative permittivity in the medium. In this case, the speed of light in the medium, which is equal to 1 upon under root mu into epsilon, is going to be equal to 1 by 2 into under root mu naught epsilon naught, right? And this is the value c. Now given that the medium is non-magnetic, the permeability of the medium will also be mu naught, right? So this is mu naught, and we can write the permittivity as the relative permittivity ER2 into epsilon naught. And can you see from here we will get the value of the relative permittivity of the medium to be equal to 4, right? So what's the ratio? Well, the ratio is going to be 1:4, and in this case option C is the right option. Next, we have an easy problem based on polarization of light. Now in this case, what's happening is that an unpolarized light passes through a polarizer A, And then behind A there is one more polarizer B that is kept. And it has been observed that the intensity of light coming out of the polarizer B is I by 2. Now there is one more identical polarizer C that is kept between A and B. And now what happens is that the intensity beyond B is found out to be I by 8. You have to find out what is the angle between the polarizer A and C. As simple as that. Now think about this. When the unpolarized light of intensity I passes through A, then the intensity will become I by 2. And in the first case, according to the question, this light, when passes through B, the intensity remains I by 2, which means that the transmission axes of the polarizers A and B are parallel, right? And now another polarizer C has been introduced in between A and B like this. Let's assume that the angle is theta. In this case, we know that the intensity of the light is reduced to I by 8. And we know that intensity is I naught cos square theta, right? So after passing through polarizer A, the intensity is I by 2. And if the angle theta is 45 degree, then in that case, the intensity through C will be I by 2 cos square 45 degree, that is I by 4. And again, when it passes through B, where the angle between the polarizers C and B will also be 45, then the intensity will be I by 8. So theta in this case should be 45 degree. As simple as that. So option C is the right answer in this simple problem. According to this problem, the angular width of the central maxima of the diffraction pattern produced using a single slit of width 1 micrometer is observed to be 60 degree. Now the same monochromatic light is used to produce the patterns of YDSE by making another identical slit near to the first one. Given that the distance of the screen from the slits is 50 centimeter and the fringe width to be 1 centimeter, you have to find out the distance between the centers of the slits. So an easy problem, right? Based on diffraction and YDSE. Now first, with the help of angular width, we can find out what is the wavelength of the light used. Can you see from the diagram, this angle theta is going to be equal to 30 degree. And at the location of the first minima, we know that in diffraction pattern, the path difference, that is d sine theta, must be equal to lambda, right? So lambda will be equal to d, which is 1 micrometer, that is 10 raised to the power minus 6 into sine 30, comes out to be 5 into 10 raised to the power minus 7 meter. And now we can apply the formula for fringe width to find out what is the value of d dash, right? So in this case, we know that the fringe width is 5 centimeter. So this is going to be 5 by 100. And this will be equal to 5 into 10 raised to the power minus 7. Let me verify if the fringe width is not 5 but 1 centimeter, my bad. So this should be 1. 1 by 100 is equal to the wavelength into the distance, that is 50 by 100 in meter, divided by d dash. From here we will get the value of d dash to be equal to 25 micrometer. So for this problem, the correct option is option A. Let's solve this problem based on Bohr's atomic model, which majority of the students found to be hard. So when the electron makes the transition from the higher orbit to the lower orbit, then it emits a photon corresponding to the energy difference of the two orbits, right? And in that case we know that 1 upon lambda, where lambda is the wavelength of the emitted photon, is equal to Rydberg constant 1 upon nf square minus 1 upon ni square, right? So when the electron is making the transition from the nth orbit to the ground state, that is n is equal to 1, in that case the wavelength of the emitted photon has been given to you, right? Which is this guy. So this is equal to R 1 upon 1 minus 1 upon n square. Make sense, right? Now how do you proceed from here? Well, in the problem statement it has been mentioned that the de Broglie wavelength of the electron when it is in the nth orbit is lambda n. So we know that the de Broglie wavelength is h upon p, right? And in the nth orbit, this is going to be lambda n is equal to h upon m into v, and this v is the speed of the electron in that orbit. Now we know that the speed is inversely proportional to n, right? Which makes lambda n to be directly proportional to the n. Make sense? Right? So what we can do is say, okay, from here we can say that n is some constant c into lambda n. Why we are doing that? Because now we can put the value of n from here to this equation. So this equation becomes Rydberg constant 1 minus 1 upon c into lambda n square. Correct? So you can see from here what we have done. Okay, it should be c square lambda n square. Alright. So look from here what we have done. We know that the speed is inversely proportional to n. And from here we can say that lambda n, which is the de Broglie wavelength of the electron in the nth orbital, will be directly proportional to n. And then we just said that let's say n is some constant c into lambda n. And then we just substituted the value of n to this equation. Right? And now we just have to simplify this. So from here we can see that this guy is going to be equal to 1 upon r into 1 minus 1 upon c square lambda n square raised to the power minus 1. And now we know that this factor is going to be really small as compared to 1. So we can use the binomial approximation, and from there we can write this as 1 upon r 1 plus 1 upon c square lambda n square. Right? And then we can simplify this. This is going to be, this guy is equal to 1 upon r plus 1 upon c square r lambda n square. This is a constant and this is also a constant. And can you see from here, this comes in the form a plus b by lambda n square. So from here, for this case, we found out that option A should be the right option. So the series limit of the Lyman series will be obtained when the transition happens from n is equal to infinity to the ground state. And the series limit of the Pfund series will be obtained when the transition happens from n is equal to infinity to n is equal to 5. Right? Do you remember the series? Lyman, Balmer, Paschen, Brackett, Pfund. So in this simple case, we can find out what is the frequency of the series limit of the P-fun series in terms of nu L, right? So we know the formula, that is 1 by lambda. So we know that 1 by lambda is R Z square 1 upon N final square minus 1 upon N initial square, right? So for the case of the Lyman series, we have the frequency to be equal to nu L, and we know that the speed of light is lambda into frequency, right? So we can write this guy as frequency is equal to R Z square C. In that case, this is nu L, and this is going to be 1 by 1 minus 0, right? And now let's do the same thing for the series limit of the P-fun series. In that case, let's say that the frequency is nu, and this will be equal to Rz square C 1 upon 5 square minus 0. And can you see from here, the relation is nu L by 25. So in this simple case, we found out that option D will be the right answer. Tell me something. If the collisions are perfectly elastic, then how come there is a loss of energy? Well, the kinetic energy before and after the collision remains the same of the system. But in the problem statement, there is a loss of energy of neutron. Okay? So let's solve this problem, which is based on collision. Let's assume that the mass of the neutron is m, which makes the mass of the deuterium to be 2m. Let's say that the neutron is moving with the speed u before collision, and after the collision, the speed of the neutron is v1 like this, and the speed of deuterium is, let's say, v2 like that. Now to find out the value of PD, we will have to find what is v1 in terms of u. So first we can conserve the linear momentum of the system. So we will get the equation mu is equal to mv1 plus 2mv2, which will give us u is equal to v1 plus 2v2. And the second equation we can get by using the definition of coefficient of restitution. In that case, the velocity of approach will be equal to the velocity of separation. And when we use these both equations to solve for v1, we will get v1 to be equal to minus u by 3. Okay. Now let's find out what is the value of PD from here. PD is delta K by K initial, right? And we know the value will come out to be negative. So what is the final kinetic energy of the neutron? Well, this is half m into u by 3 square minus the initial kinetic energy is half mu square divided by half mu square. And this is going to give us minus 8 by 9, which will come out to be minus 0.89. Okay, this is the magnitude. And if you observe, then in the options, there is only one such option that matches the value of PD. So no need to solve for PC. Directly we can take option A as the right answer. So the silicon diode is connected in the forward bias connection in this circuit. So what will happen? Well, when the cut-in voltage is reached, then with small change in voltage, the current is going to increase rapidly across this non-ohmic conductor, right? And we can find out the reading of the ammeter, that is current in the circuit, by simply applying the formula, that is V minus V cut-in divided by R. where V minus V cut in is the potential difference across this resistor, right? And cut in voltage is 0.7 volt. So this is 3 minus 0.7. That is 2.3 volt is the potential difference across this resistor. And if we use the formula, then I is going to be equal to 2.3 divided by 200. That is 11.5 milliamp. So in this simple problem, we can see that option C is the right value of the reading of the ammeter. Although the tagged concept in this case is communication systems, but I would say this question is simply based on unitary method. So, what is the total available frequency that we have? Well, we are only utilizing 10% of 10 gigahertz. That is 10 by 100 into 10 into 10 raised to the power 9. And each channel has the bandwidth of 5 kilohertz. So divided by 5 into 10 raised to the power 3 will be the number of channels. Yes? And if you simply solve this, you will get the value to be equal to 2 into 10 raised to the power 5. So as simple as that, I think this is the easiest problem in the whole paper, and option C is the right answer. Now for this problem, based on potentiometer, you have to find out the internal resistance of the cell. So what's happening? Let's see. When a cell of EMF E is connected in the secondary circuit, then the balancing length is obtained at 52 centimeter along the potentiometer wire. And you know that the potential drop across the wire is uniform in the case of potentiometer. So we can say that for this case, E will be proportional to L1, where L1 is 52 centimeter. And now a shunt resistor is connected across the cell such that the secondary circuit is complete and there is some current I in that circuit. And now the balancing length is obtained at 40 centimeter along the wire. And we know in this case E minus IR will be proportional to L2, right? Where I is going to be E divided by R plus R. And with this, we know that the internal resistance will be equal to the shunt resistance into L1 minus L2 divided by L1, right? And let's put the value. So this is going to be 5, 52 minus 40, that is 12 divided by 40 ohm, and this is 1.5. So in this simple case, the internal resistance of the cell is 1.5 ohm and option B is the right option. According to this simple problem on meter bridge, when the two resistances are interchanged, then it has been given that the balance point on the meter bridge is shifted by 10 centimeter to the left. If the summation of the resistances of the two resistors is 1 kilo ohm, you have to find out the resistance of the left resistor. So let's make a simple diagram to understand this problem. Let's assume that this is the first resistor, this is the second one, and this is the meter bridge wire. Let's say that this one is R1 and this one is R2. We have to find out the value of R1. So in the first case, let's say that the balance length is X, right? Which makes this one as 100 minus X. We are taking X to be in centimeter. Now we have one equation already, that is R1 plus R2 is equal to 1000. Let's say this is equation 1. And we can apply the condition for the Wheatstone bridge to obtain the second condition. That is R1 into 100 minus X is equal to R2 into X. Right? And now, when the resistors are interchanged, when this is R2 and this is R1, then the balance point is shifted to the left by 10 centimeter. So the new length on the left hand side is going to be x minus 10, and this is 110 minus x. So this will become R2 into 110 minus x is equal to R1 into x minus 10. And when you solve this, you will get the value of x to be equal to 55 centimeter, which will give you the value of R1 to be 550 ohm. So there we go. In this problem, we can see that 550 ohm is the right value of the resistor on the left slot.